we're trying to get this to render to our GUI. So we have the GUI class. We made a Raymarching panel, and we've added that panel to the GUI. And let's see, the panel has got a variable that's going to store the sign distance function for the scene and a camera. So we need a method that's going to actually render this SDF on the screen. And right now, we're just wanting to loop through all the pixels on the screen and try to detect if the object, in this case all we have is a sphere, is visible at that point on the screen or not, and draw the correct color there. And then we can add shading and fancier stuff after that if we get this to work. So let's start with a method that renders the scene. Let's do that. Let's add a method here, and yes, it can be public. Public void render scene. Okay. So we're going to use information about the camera, so where the camera is located and which direction it's facing. It's forward vector, direction vector, and it's up and right vectors. And then it also has, some kind of ratio for how the ratio of the width to the height of the screen. I guess we could think of that ratio. But we need some way to access the ratio. So maybe instead of making this private, maybe we should make it public. But I'm not going to do that because they don't like that on the AP test. So let's just add a getter for this ratio, I guess. In the camera class here, real quick, we're going to do a public double get ratio. Return ratio. Yes, we could. Yeah, that's fine. Okay, cool. Now we can go to the Raymarching panel, and in our render scene, we want to do a loop through all the pixels on the screen. So we have this buffered image that's going to be our screen that we're drawing to. So let's go ahead and set up a nested for loops that it's going to loop down all of the pixels in a row and then all the rows going down. So let's do for int x, so x would be the column number, equals 0, x less than, that would be the width of the image, image dot get width, x plus plus. And for int y equals 0, y less than image dot get height, y plus plus. Okay. So we have to imagine that image kind of floating in space in front of the camera. So we got the camera is at a single point in space, and we've got this rectangular image that's floating in front of it. And we need to figure out the vector, the ray that goes from the point where the camera is to the pixel on the screen with the x, y coordinates. So basically, we want to start at the camera's position and then move forward by the camera's forward vector, and then we need to move right or left according to the x coordinate of the pixel on the screen, and then up and down according to the y coordinate. And we're going to move along the camera's right vector for the right and left, and along the camera's up and down vector. So let's see if we can figure out this vector math. So let's create a new vector 3 that is going to be this ray that extends out from the camera to the screen. So it's actually instead of creating it from the constructor, we're going to call those methods to create it. So we're going to start with the camera's position vector, which we can get with the get position, and then we want to add onto that the forward vector. So imagine that the distance between the camera and the screen is that forward vector. So we want to move from the camera onto the screen by adding the forward vector of the camera. Camera dot get direction, I think is what we called it. Okay, so now our ray is pointing from the camera directly to the center of the image that's hovering in front of it. So now we need to move to the left or right based on which x coordinate the current pixel is that we're trying to point at, that one particular pixel. We're going to land on that pixel. So we can figure out as like a percent how far along the screen from the left and right that x coordinate is, but we want to do it based on the center, where like 0 is the center, so pixels to the left of the center are negative and pixels to the right of the center are positive. So we want to take that x and we want to subtract the center to kind of shift it. So the center is going to be half the width. Get width divided by 2. And let's do this as a floating point operation. And then we want to take that and divide it by the entire width of the screen, if I'm thinking about this correct in my head. Let's see. So we're going to take that and divide by image dot get width. And then we can store that for now. Let's do a double, what would we call this? X ratio. Okay. Move this so you guys can see it. All right. I did an underscore. This is in Python. X ratio. There we go. Okay, and so that's how much we want to scale the right vector of the camera to get to this x position on the screen. But we also want to scale it by the camera's ratio. So let's try that real quick. So the ray, what we're going to do is we're going to add onto this ray the camera's right vector scaled by or we want the get scaled, I think, because we want this to return a vector. So we did get scaled. Is that what we did? Get scaled, I think we did both. No?
Are you saying the normalized?
No, I want to scale it, but the scaled, we have to look at my vector 3 class here. The scaled one, does it change? Oh yeah, we do have get scaled, double S. Okay, so yeah, this is the one that we want because we want to return a new vector that's been scaled. So get scaled. And then the amount that we want to scale it by, oh, I just need this semicolon at the end. Okay, so we want to scale it by the x ratio, but also by the camera's ratio, I think. Sure. camera dot get ratio. Okay, so that moves the tip of the ray right and left along the screen until it's pointing at the current pixel. Now we need to move up and down on the screen until it's pointing at the correct pixel. So
You multiplied the x ratio by the like aspect ratio. Is that what?
yes,
Okay.
I did. I think that's what we want to do because we want the screen to be wider than it is tall, and the right vector is a unit vector to start with. So we want to stretch it out. We'll leave the up vector as a unit vector. Yeah, maybe. Okay. So now we want to basically repeat this, but for the y's. So double y ratio is going to be y minus image dot get height divided by 2.0, and then divide that by image dot get height. Okay. Now here's the thing: the y's, though, again are backwards. So with this, the y's that are above the center are going to be negative, and we want that reverse. So let's, because we could reverse the subtraction here, or we could just multiply by -1. So let's put a negative on here to reverse it, to fix it so that the coordinate system is not upside down.
Oh, it'll let you just put a negative?
You can, yes, if it's part of an expression, yeah, you can just put a negative, and that'll.
Python where it make you multiply by -1 and it wouldn't let you?
I'm not sure. It might be a language like that, but yeah, no, Java you can just negate something. It's a unary operator that basically is like multiplying by -1. Yeah. All right, so now we're going to take the ray and we're going to move it by adding the camera's up vector. Camera dot get up dot get scaled, scaling it by the y ratio. Okay. So now this ray vector should be the vector that points from the camera to the pixel on the screen. So now what we want to do is pass this ray vector to a method that's going to perform the Raymarching itself and move that vector through the 3D scene until it hits something in the well, it either will hit something on the SDF function, or it will pass everything by and go to the background.
You add the camera position vector with the camera direction vector, right?
Correct, yes.
But I think I might be confused. Is that a vector that's supposed to be starting from where the camera is and pointing in the direction?
So the direction vector.
Oh, the camera's at the origin?
No, the get direction, the direction vector, the forward vector is in like standard position. So its initial point is the origin. So it doesn't have the embedded information about the location of the camera, right? So you can move the camera, change the camera's position without changing its direction. Its direction will maintain, be the same. Does that make sense?
Yeah, because.
And then when you add the position, add the direction onto the position, now you have the vector that's pointing from the camera's position to the direction it's looking, right? You're like translating, because adding vector is sort of like translating a vector.
I got you. I was thinking like it was as if like the camera position vector points from the origin to where the camera's position is.
That is true.
So then adding the direction would just get you a vector that points from the origin to the camera's position plus direction. I thought we wanted it to point from the camera's position to in the direction of the camera's direction, but I think that was like
Okay, let me think about it. Maybe you are correct. So we want
I got lost somewhere through there, so you got to
Ray.
take it with a grain of salt. But
Hold on, let me think about it because I could be wrong. Let's try it.
no, take it with a grain of salt.
So the ray, yeah, let's not add the position to the ray just yet. We want to keep them separate so that we can scale the ray, and then we'll have to add it onto the camera's position when we're calculating the point in the 3D space that we need to pass to the assigned distance function. But yeah, it's probably better to keep them separate for now. So we'll start the ray as just the camera's direction. Okay, and then we'll use the right and up vectors of the camera to get the point on the screen. That seems good. Okay, so let's right here we're going to do the Raymarching, but we need to write a method for that. So let's add a method in here that takes. I guess I'll have to take two vectors. I'll have to take the starting position and the direction vectors, and then this method is going to return. It should return a material because we want to know what material that ray is going to hit. And I guess it could return the actual SDF. I think let's just go with the material for now. So let's create the function that says probably can be private, and it's going to return a material, and let's call it Raymarch, and we're going to take a vector 3 for the start position and a vector 3 for the direction. Okay. So in this, we're going to have to loop, and each time we want to calculate that 3D point in space that's that the vector is pointing towards, and then pass that point to the assigned distance function for the scene, and see if it is if it's positive. That means we need to keep going because we haven't hit anything yet. If it's close to 0 or negative, we need to stop because that means we've hit something. We also want to make sure that we check to see if we have gone past some maximum distance, and at that point just assume that they're not going to hit anything and return some background material. Okay, so we'll probably want a while loop, and let's create a Boolean variable. Let's call it marching. Marching equals true, so we can stop the loop when either we've gone too far or we've hit something, and then we can just say while marching. All right, so let's calculate that point in 3D space. So now that's going to be where we do the camera's position, or the start position, and we add the direction vector vector to it. Okay. Oh, I have to give it a name. Vector 3 point equals start add direction. All right, so this will be, and the very first time, that should be the point directly on the screen itself. So now we want to check this point to see with the scene SDF if we've hit something. So we can call and see if scene.get distance to that point, if that is less than whatever our we're determining our minimum distance is, which we should probably make a variable for that. So let's actually go up here and let's just do a private static final double min distance equals, I don't know, 0.01, something like that. Something that's close to 0 that we're counting basically as 0, because with floating point, you know, we're never going to be exactly 0.
This is a competition to see how many keywords we can get.
Yeah. Yeah, that's a lot of... Okay, so minimum distance. So if the point is less than the minimum distance away from this object or an object in the scene, then we've hit something. So we're going to just return the material that's there in the scene. So that's where we can call scene.getMaterial and pass in the point, so that the renderer can render that material at that point, which we'll probably have to add another method if we're going to add like shading and shadows and that kind of stuff. But for now, that's that should be good, I think. And okay, so if we don't hit something and return, then what we need to do now is move the ray forward. We want this by this minimum distance. So actually, let's store that distance, so we're not calling that method twice each time, because that's going to slow things down. So let's say double distance equals scene.getDistance. Store that, and then just use the value we stored. Because if we call scene.getDistance again, if it's a complicated scene, that's where a lot of the time is going to be in calculating that distance. Okay, so we didn't hit anything yet. So now we want to move the ray forward as far as we can, and we know we can move it forward by this distance because we're not going to hit anything if we move forward that distance. So to move it forward, we just need to scale the direction vector by that amount and add it onto how are we going to do that? So we can, if we want to add a vector that's that size onto it, so it's still facing the same direction, but its length increases by that amount. We can't just scale it.
We can't scale. Do we have a function that tells us the length of the vector?
Yeah, that's the magnitude. So we could normalize it. Okay, I think a straightforward way to do it would be to take the ray and add onto it. Ray equals ray dot add onto it the ray normalized. Do we have get normalized? And then scaled. Get scaled by the distance. Wow, what is that? Can I find some? Oh, it's not ray, it's called direction, sorry. I'm going to change it from direction. Well, no, I guess we'll use direction, that's fine. Direction equals direction, add direction, okay. Get scaled, yeah. Stop. Okay, that should move the ray forward. By the right amount. It's probably not the most computationally efficient way to do it because we're normalizing the vector every time. But oh well.
If we're moving the vector,
yeah.
If just like scaling it every time, could we just normalize it once and then just?
Yeah, we could keep track of like the total distance.
I guess that might take just as much.
Yeah, I mean normalizing is slow because you're dividing and you're square rooting, and those are slower operations. So this is probably going to be slow. I guess we could speed it up if we normalize the direction to begin with, and then just reuse that same normalized direction. Yeah, that might be better. And then just keep track of like a total distance. Let's try that. So we do double total distance equals 0. We have the start and we have the direction. Just to make sure, let's normalize the direction. So direction dot normalize. Do we have a normalized? Or we only have get normalized. Okay, so we'll have to say get normalized direction equals direction. Get normalized, we'll just do that once. And then, so the point is going to be start add direction dot scale total distance. Total distance. What? Oh, get scaled. Okay. Last. Vector 3 point equals start dot add direction dot get scaled total distance. And then distance equals scene dot get distance point. We want to add total distance plus equals distance. I guess we do this after we see. Here, total distance plus equals distance. And then we don't have to do all of this. And we can check to see if total distance is larger than the max distance, which we haven't defined yet. Max distance. Then we're going to stop. We'll just return the background material. Okay. Maybe that'll work. Max distance. Yep. So let's add this max distance variable and this background material up here where we have minimum distance, private, static, final, double, max distance. I don't know what that would need to be. Let's try 1,000. That's probably way more than it needs to be. Let's do 500. And then we need a background material. Private material, background material. Okay. So we need, I guess in the constructor here, we'll just assign that background material. Background material equals new material color dot blue. I need my background blue, like the sky. Background material, new material. Oh, too many parentheses. Okay. Don't capitalize the G. Background material. There we go. Okay, so Raymarching panel, paint component, G, image, render scene. So now, after render scene, in this loop here, now we can call this Raymarch and get the material to render. Material material equals Raymarch, and give it the camera position for the starting position, get position, and give it the ray for the direction. And then now that we have this material, we want to draw it, that pixel on the screen, whatever this color is. So image dot set RGB, x, y are the coordinates of the, and then this is the color, so this is going to be material dot get color dot get RGB. Okay. And then after the scene has been rendered, when these for loops are done, we need to call repaint so that the display will update. Okay, I think we might be almost ready to test this. We just need some way to call this method from the GUI, so we could do an on-click event. So you click on it and then it renders it. Let's try that. So if we have an error somewhere. Where's this error? Oh, what is this? Oh, we have a we need a return here. I guess we'll just return null. It shouldn't ever make it here because we're either going to return one of these two eventually, hopefully, but okay. So we go to the GUI, go to our panel, go to events, go to the mouse clicked event, and we'll call our Raymarching panel 1 dot render scene. Is that what we called it? And that should update it. Okay, what are the odds that we see a red circle on a blue background? I don't know. Alright, if I click this, maybe it'll work. Oh my gosh, I can't believe it worked. How about that? That's crazy. Okay, well, hey, we're off to a good start then. So next will be the shading, but we're out of time for today, so obviously we'll stop there.